डियर स्टूडेंट्स, आप आ गए अपने बहुत ही प्यारे प्यारे चैनल पे केमिस्ट्री बाय प्रोफेसर सिंपल राजेंद्र शुक्ला. स्टूडेंट्स, बेसिक आइडिया बिहाइंड मेकिंग दिस वीडियो इज, बच्चे हमेशा बोलते रहते हैं मिस टॉपिक तो हो गया लेकिन अब पूरे टॉपिक का रिवीजन एक स्ट्रोक में कैसे करें. तो आज मैं एक पूरा टेक्निक बता रही हूँ, पूरे टॉपिक को कैसे एक बार में रिवाइज किया जाए ये देख लेते हैं. टॉपिक का नाम है थर्मोडायनेमिक्स एंड हम पूरा एक फॉर्मूला इस टॉपिक का देखेंगे, किस तरह से मैथमेटिकली हम इस पूरे टॉपिक को एक स्ट्रोक में रिवाइज कर सकते हैं. लेट अस स्टार्ट माय डियर स्टूडेंट्स. पूरा फोकस उस बात पे रहना चाहिए जो मैं लिख रही हूँ और जो मैं बोल रही हूँ, पूरा ध्यान से उसको सुनना है और जहां जहां जरूरत लगेगी एक पेन पेंसिल पेपर लेके बैठना है और नोट करते जाना है. सो लेट अस स्टार्ट. सबसे पहला बेसिक थिंग, the word thermo means heat and dynamics simply mean the science of motion. The science of motion. Or we can say it is the transfer or the flow, transfer or flow of heat. हीट के लिए मैंने ये सिंबल यूज किया है और थर्मो में ये सिंबल मैं डायनेमिक यानी कि चेंज के लिए भी यूज करूंगी. सो डोंट गेट कंफ्यूज्ड. फिलहाल ये सिंबल हमने हीट के लिए यूज किया है. थर्मो, हीट. Symbolically, I will say it like this. Next is, we come to the term energy. Why? क्योंकि हीट भी एक फॉर्म ऑफ एनर्जी है. थर्मो में हम हीट एनर्जी पढ़ रहे हैं. हीट इज अ फॉर्म ऑफ एनर्जी. तो साथ में ये समझ लें व्हाट इज एनर्जी. एनर्जी इज नथिंग बट द कैपेसिटी टू डू वर्क. Energy is capacity to do work. Try to learn with me because this is a revision. So you know majority of the things. In fact, you know all the things. And we know energy is directly linked to do the work. It is capacity to do work. That means energy, I can say, is directly proportional to work. That is, I can mathematically write like this. That is, larger the system has a energy. किसी भी सिस्टम में जितना ज्यादा एनर्जी है उतना ज्यादा वो वर्क कर सकता है और जितना कम एनर्जी है उतना कम वर्क करेगा. मोर द एनर्जी, more the capacity to do the work by the system, and less the energy, lesser is the capacity of any system to do the work. So lesser the energy of a system, lesser is its capacity to do the work. Then once we understand energy, we should also know what are the various forms of energy. So let us see what are the various forms of energy. So one of the energy which you have been learning in chemistry, most common, is the chemical energy. What is the chemical energy, students? Just think, आप साथ साथ में आंसर दे सकते हैं. Chemical energy is nothing but the energy of chemical substances. Energy of chemical substances is called chemical energy. Energy of any chemical substance. Then we go to another form of energy, which is electrical energy. Oh, just now we learned conversion of electrical energy to chemical energy to electrical energy in our previous topic, which was electrochemistry. By electrical energy, students, we simply mean energy of the voltaic cell, that is the galvanic cell, the electromotive cell. Its energy is, we are referring to electrical energy on broad basis. Then obviously we can have kinetic energy. Kinetic energy, also called external energy, also called thermal energy, which is nothing but energy by motion, energy of a body by virtue of its motion. Then जैसे काइनेटिक एनर्जी दिमाग में आता है, फटाक से दिमाग की बत्ती जल जाती है. ओ, there can also be potential energy, which I can say energy of a body by virtue of its position. So energy by virtue of position is the potential energy. What else? There can be radiant energy. What is that? What is the radiant energy? Very simple. Majority of you must be knowing it. Radiant energy is nothing but the energy due to light, the light energy, the radiations coming out of the various kinds of energy, the radiant energy, the radiations, and the light. Like we can say electromagnetic radiations. And then our topic, the heat energy. And its dynamics we are learning in this topic. And heat energy is nothing but the thermal energy. Heat energy is nothing but the thermal energy, students. And thermal energy, we know, like, hot, how energy flows from hot to cold. And that is how we learn the transfer of the thermal energy. So what we just did is nothing but forms of energy. Forms of energy, where we did these many forms of energy. Now we move ahead. Next comes the very important factor which we just discussed in the definition of energy, capacity to do work. So how to define work in just one line? Work is nothing but the organized form of energy. Work is nothing but the organized form of energy. When I repeat, just see to it you repeat with me, and 90% of the things can be learned with me itself. Work is nothing but the organized form of energy. That is, energy, we just write proper definition, what we learned in physics. Energy by which, energy by which a body, work is organized form of energy, that is energy by which a body is displaced through the distance d. Be attentive. Body is displaced to a distance d by applying a force which we are denoting by F. Now we come to next. Let us just understand it mathematically. We call it PV work, which I also refer to the mechanical work, which I can say is nothing but P delta V. And how is that true? Let us see. We know, students, work is nothing but force into displacement. Now, we all know that PV, P into V, is nothing but product of pressure and volume. Now see, I know, you also know, pressure is force upon area. So I substitute here force upon area into volume. Now I know area is centimeter square, so I consider it d square, as d I have taken for distance. And v is centimeter cube, so I take it as d cube. And I substitute it here, force upon d square into d cube. As a result, I get F into d. So comparing this, work is force into displacement with P into V is nothing but force into displacement. I can conclude immediately that P into V is nothing but work, which I call as pressure, volume, work. I hope this is clear to you. Now we move ahead with the sixth point. Let us see what it is. The sixth point is, in when whatever we study, the different kind of processes which we do on a particular object or a particular area or whatever, what do we call it? So that is known as system. The important terms which you should know before understanding thermo is system. I'm just revising a little bit, and then we go to the mathematical formulas directly. A specific portion of universe, a specific portion of universe under thermodynamic study. You can repeat with me. System is defined as specific portion of the universe under thermodynamic study or thermodynamic consideration. Now, what I mean by thermodynamic study and thermodynamic consideration, meaning the portion of the universe on which I will be understanding, or I'll be studying, or I can say I'll be observing the various kinds of properties like, temperature, pressure, or volume. How do they vary or how do they change? Not only that, I can also say that system is usually a chemical reaction under observation or a gas enclosed in a cylinder. Now, when we leave the system, just exclude the system, and then whatever remains is called surrounding in thermodynamics. So, what is a surrounding? The remaining portion of the universe. The remaining from where? Remaining from the system. यानी सिस्टम ने जितना भी जगह ले लिया वो तो सिस्टम है जिसपे हम कोई फिजिकल चेंज या कोई केमिकल रिएक्शन या किसी गैस पे कोई प्रेशर, वॉल्यूम, टेम्परेचर का इफेक्ट पड़ रहे हैं, और उसको छोड़ के व्हाटएवर रिमेन्स, जो भी बच गया, द रिमेनिंग पोर्शन ऑफ द यूनिवर्स. The remaining portion of the universe, that is excluding the system. You can repeat with me. The remaining portion of the universe excluding the system is called surrounding. And the surrounding may or may not be under thermodynamic consideration, may or may not be under observation. So may or may not be under thermodynamic observation or thermodynamic study, or I can call it thermodynamic consideration. That is, surrounding में क्या changes हो रहे हैं? I may observe it, I may not observe it. Okay? Next. Another important thing which comes into picture is the boundary. The boundary. Now, what's a boundary? What is a boundary? The terms are boundary is something which is real or imaginary. Learn the terms real or imaginary. It is rigid or non-rigid. It is conducting or non-conducting. Revise. Boundary is rigid or imaginary, real or non-rigid, conducting or non-conducting. Revise in sequence. Boundary is real or imaginary, rigid or non-rigid, conducting or non-conducting, across which matter and energy can flow from the system to the surrounding and vice versa. Once again, I repeat, boundary is real or imaginary, rigid or non-rigid, conducting or non-conducting, across which matter and energy can flow from the system to the surrounding and vice versa. The matter in a system is separated from the surrounding by a boundary. Say, for example, I take a cup of hot water under thermodynamic consideration. Now, the water in the cup is the system. This is system. This walls of the cup is the boundary, and everything excluding this cup and that hot water is the surrounding. So boundary basically defines limit of the system. Boundary, very self-explanatory line. Boundary decides the limit of the system. Boundary decides the limit of the system. Very particular intelligent line. Boundary decides the limit of the system. Boundary is the wall. Boundary is the wall. Boundary is the wall that separates the system from the surrounding. Let us move ahead. Yeah, we come to the 9th point, and that is the phase. Many times this term will come, the phase. What does it mean? It is a part of system. It is a part of system which is chemically homogeneous. Don't misunderstand. I am not defining homogeneous phase. I am saying phase is the part of the system which is chemically homogeneous, physically distinct, meaning you can understand which phase is where. आप पहचान सकते हैं कि कौन सा फेज है और कौन सा फेज दूसरी जगह और कौन सा पहली जगह है. And when I say physically distinct, the moment I say physically distinct, it is very clear they are mechanically separable. So physically distinct means they are mechanically separable. When I will say mechanically separable, when the system is having more than one phase. Mechanically separable. So phase is part of system which is chemically homogeneous. जैसे एक वेसल में मैंने ऑयल लिया और पानी लिया तो मैं एकदम सही देख के बता सकूंगी कि कहाँ पानी है और कहाँ पर ऑयल है, क्योंकि पानी के सभी पार्टिकल्स का केमिकल कॉम्पोजिशन होमोजेनस रहेगा, अपीयरेंस सेम रहेगा, फिजिकली डिस्टिंक्ट रहेगा, और ऑयल का केमिकल कॉम्पोजिशन अलग रहेगा और उसका फिजिकल डिस्टिंक्ट जो फीचर है वो मैं क्लियरली देख के समझ सकती हूँ कि ये ऑयल है. So that is the meaning of phase. So when I say oil in water, I mean there are two phases in it. One is the oil and other phase is the water. So I can say phase is a layer of matter in which distribution of matter is uniform. I can say in one line, phase is a very interesting line. Phase is layer of matter like a layer of oil and layer of water. So phase is layer of matter in which distribution of matter is uniform. And we come to a very interesting point now. We did system, we did surrounding, we did phase, we did boundary. Now we combine the two and we write what we mean by universe, system plus surrounding. This is the universe. If I want to study universe as a system, if entire universe is a system, if we say entire universe, let entire universe be the system, then there are or there is no surrounding. If entire system you consider as universe, then there is no surrounding. Next, let us see what are the various types of system. Okay, and I first give it diagrammatically and then we will move ahead with the points. Types of system. So first of all, what I'm doing is I'm taking 3 beakers and we'll just see what's the difference. This is our one of the beaker. This is another, and this is the third one. Now, in all the beakers, what I'm taking is dilute H2SO4 and zinc metal. So I put dilute H2SO4. In this vessel also I'm taking dilute H2SO4. And in this vessel also I'm taking dilute H2SO4. So this is the dilute H2SO4. And same thing I took here. Dilute sulfuric acid. And my dear students, we took the same thing here, that is dilute H2SO4. Now what I do is, to all of them, I am adding zinc metal. Say these are the pieces of zinc metal. These are the pieces of zinc metal. These are the pieces of zinc metal. So that's the zinc metal. This is the zinc metal. Same way here, this is the zinc metal. Now, what I do next is, I keep this vessel open. This is the open vessel. I call it open system. And what I do in the next one is, I close it with a lid. And I call it a closed vessel. And in the next one, what I do, students, is I, insulate it. I just cover it with an insulating material, say a rubber, and the entire vessel is insulated. And say I took a thermo flask, completely insulated, and I call it a isolated vessel, so I call it an isolated system. So these are the categories which I took. We took 3 types, and something has already started, going through your mind, and you understood the 3 system, the types of system. The 3 systems are the open system, the closed system, and the isolated system. Now see, now we know when zinc reacts with H2SO4, we will get ZnSO4 plus H2 is liberated. Correct? H2 is liberated. And with H2, what else is liberated is the heat energy. Now, when they react from here, H2 gas comes out. And also the heat is given out. Heat is also given out. So heat is given out. In this, heat is given out, true, because it can just go out from the sides walls of the container. But H2 is blocked inside. It cannot come out. And here, H2 is inside, and also heat cannot come out. Everything is inside. Now, heat is a form of energy. Heat is a form of energy. And H2 is a form of matter. Matter I represent by M, and energy I represent by E. E. Coming out. And here I see nothing is coming out to the surrounding. So I conclude my points, and they are the very first. This system, open system, can exchange matter, and hence change in matter will take place, and delta M is not zero. Delta is change in matter, that is change in mass. Because it can exchange mass, you can see here, H2 is coming out. So with H2, some mass is getting eliminated from the system. So delta M is not zero. And you can see heat is also coming out in the energy in the form of heat. So delta E is also not zero. So open system is a system which can exchange both matter and energy with the surrounding. Students, if you see here, this one, then you find that it can exchange heat energy. You see here heat energy, but it cannot exchange matter, because all hydrogen you see is struggling inside the vessel only, and it cannot come out. So change in matter is not taking place because it cannot exchange matter with the surrounding, but it can exchange energy with the surrounding. So delta E is not zero. And this system, isolated system, can exchange neither matter nor energy from the surrounding. So delta M zero and delta E also zero. Next, temperature. Temperature, you see heat is coming out, so temperature will change, but temperature may not change also. So I can write temperature, that is I am denoting by T, T is temperature, may not change. When I say may not change, means may change also. Now when will it change, when it will not change? It will not change when whatever amount of heat is going out from here, that much I am supplying from outside. यानी ये जो हीट यहाँ से निकल रहा है, अगर उतना ही मैं हीट बाहर से इसमें डाल दूं तो टेम्परेचर में नॉट चेंज, और अगर मैं इसमें बाहर से बिल्कुल भी हीट एनर्जी सप्लाई नहीं करूं तो टेम्परेचर विल चेंज. सेम थिंग हियर, टेम्परेचर मे नॉट चेंज. कैसे? सेम थिंग. If whatever amount of heat energy the system is throwing out of it, if that much I supply from outside, because it is just closed vessel, closed with a lid, that's all. So I can supply heat energy and then temperature will not change. But if I don't supply heat energy, then the temperature will change. Here, I cannot supply anything. Temperature always changes. ऑलवेज चेंजेस. ऐसा थोड़ी है कि आपने थर्मस में चाय रख दिया तो जीवन भर वो ठंडा ही नहीं होगा. हाउ इज दैट पॉसिबल? मतलब थर्मस में भी पार्टिकल्स कोलाइड कर रहे हैं और कंटिन्यूअस एनर्जी छोड़ रहे हैं. खाली वो एनर्जी सराउंडिंग में नहीं जा पा रहा है, ना ही सराउंडिंग से आप कुछ उसमें डाल सकते हैं. इसलिए टेम्परेचर ऑलवेज चेंजेस. नेक्स्ट, temperature always changes in an isolated system. Next comes pressure. Pressure and volume will change. Changes in an open system. Obvious है, देख रहे हैं आप, हाइड्रोजन गैस है, जा रहा है बाहर, ओपन वेसल है, प्रेशर एंड वॉल्यूम दोनों चेंज होंगे. Here no change in volume. Why? Just think. No change in volume क्योंकि मैटर बाहर नहीं जा रहा. So no change in V, but pressure changes. Here, here, no change in volume because जो भी मटेरियल है वो सब अंदर ही है, बाहर कुछ निकला ही नहीं है. प्रेशर may change. Okay, now we have just written the three differences, so I'm just changing that. Okay, so this was our third, and just take it as first point for all, second for all, and third for all. Now next, another way to classify systems is, that was types of system. Point 12 was types of system on the basis of exchange of matter and energy. Now again I'm writing types of system, but on the basis of, we have changed the base of classification, and now it is on the basis of phase and composition. On the basis of phase and composition. So what are the types of system on the basis of phase and composition? So there we get two categories. One of them is the homogeneous system. And the other category is the heterogeneous system. Homogeneous system and the heterogeneous system. Just points. Homogeneous system means single phase, like entire oil in the vessel. पूरे के पूरे vessel में सिर्फ oil है. Single phase. you'll find more than one phase. Like oil and water, more than one phase. यूनिफॉर्म कॉम्पोजिशन, ऑब्वियसली अगर एक ही समान है तो कॉम्पोजिशन पूरे समान का सेम होगा, सो यूनिफॉर्म कॉम्पोजिशन हियर does not have uniform composition, does not have uniform composition. Then we can say this can be like, mixture of gases. Very common example, बचपन से पढ़ते आ रहे हैं, right from childhood. Then it can be miscible liquids. Miscible liquids will form one phase because they completely mix with each other. Also, pure solids, liquids, or gases. Here, we can have oil in water, emulsions. Oil in water is nothing but an emulsion. It can be ice in contact with water. Very simple examples I am taking. Ice in contact with water. Being it sand and salt. So this is classification on the basis of the phases. Little introduction I have given you of the thermo. This will help you to understand the topic. And now I'm moving to the intensive and the extensive properties. Intensive properties and the extensive properties. Intensive properties are those which are independent of quantity. The properties which are independent of quantity or the amount of substance are intensive properties. Extensive properties are those properties which are dependent of the quantity or the amount of the substance. And I go to the examples directly. Here, first I am writing, extensive, because once I get that, rest all is done. Volume, mass, work, surface area, internal energy. You should learn. Volume, mass, work, surface area, internal energy, enthalpy, entropy, energy, heat, heat capacity, and mole. These are extensive properties dependent on quantity. And what are intensive independent of quantity? Oh, almost everything other than extensive. So I just think of different properties. Okay, temperature, mass volume हो गया इधर, तो temperature, pressure, then density, pH, viscosity, refractive index, specific gravity, surface tension, dielectric constant. Then we can also write boiling point, very simple, melting point, dipole moment, vapor pressure, specific heat. Then we can write molarity, molar heat capacity, that is Cp, Cv, normality, optical activity. So these are the intensive. So here we did the intensive, and here we have written the extensive properties. Now we move ahead. We go to point number 15. And now we just understand what do we mean by ratio of two. The ratio of two extensive properties is intensive. One more thing, students. Extensive is also called extrinsic. And intensive is also called intrinsic. And now, ratio of two extensive properties, say mass upon volume. Mass is extrinsic, volume is extrinsic, but the ratio is density, and density is intrinsic. That's the way. Now, next point. In thermodynamics, when you read the topic, you have seen, you come under the, you come across the term state of system. Let us consider state of system, so and so, and things like that. State of system is nothing but the condition of the system, which is described by its measurable properties. Once again, I repeat, state of system is defined as condition of the system, which is described by its measurable properties like temperature, pressure, volume, composition. State of system is defined as condition of the system which is described by its measurable properties like temperature, pressure, volume, and composition. These are not only called the measurable properties, they are called the measurable properties. They are also called the macroscopic properties. And they are also called the observable properties. So this is nothing but the measurable property, the macroscopic property, the observable properties, and I also call them the thermodynamic. See, terms are important. It's the same thing, but if you don't know the term, then you get confused. They are also called the thermodynamic variables, and my dear children, they are also called the state variables. So state of system is defined as condition of the system which is described by its measurable properties like temperature, pressure, volume, and composition. And when these macroscopic properties have a definite value, then the system is said to be in a definite state. When one or more of these properties or variables are changed, the state of the system changes and the system is said to have undergone a change of state. Now, before alteration, the state of system is called initial state, and after alteration, it is called the final state. Before change, I mean before alteration, before change. And after alteration, that is after carrying out a change or a process. Before change, that is before doing the process, the system is said to have the initial state, and after a process is done or an alteration is done, we call it the final state. So you must have come across various such terms. In fact, we did the entire topic in the class. I'm just giving a revision now. Now we move to the next. After the state function, we go to after the state of the system, we go to the state function, which is our, so we have done till point 16. So we just move to point number 17 now, which is our state function. We just did state of system, now the state function. State function is that. State function is the property of the system which depends only on initial and final state of the system and not on the path followed, and that are also called the thermodynamic function. Once again, I'm repeating, be attentive, try to learn with me. Once you know, I'm just doing the language of thermo. Once you know the language of thermo, I just write the different formulas, and that'll be sufficient as a revision. This is a revision I'm taking, so the format will be of a revision lecture. State function is the property of the system which depends on the initial and final state of the system and not on the path followed. And these are also called the thermodynamic function, and they are like pressure, volume, temperature, enthalpy, internal energy, mass. Next is the path function. The path function. So the path function is that, see, if I say state function depends only on the initial and final state, but not on the path followed, that doesn't mean aap fatak se bolo path function depends on path. No. Path function depends on state as well as the path. So I'm defining, just be attentive, okay? Very attentive, very attentive. Path function is the property of the system which depends on the initial and final state of the system as well as upon the path followed. Example, heat, work, heat, work, heat capacity, the path function. So they are the path functions. Heat, work, heat capacity. Next comes an important thing, and that is, sometimes I'll say, okay, system is in thermodynamic equilibrium. In the formula, when we come to equilibrium, the last formula in the thermo, when I'll be revising, you remember, thermodynamic equilibrium is basically three kinds of equilibrium. Three equilibrium at a stretch, and we call it thermodynamic equilibrium. And the three equilibrium are, one is the thermal equilibrium, and another one is the mechanical equilibrium, and the last one is the chemical equilibrium. And that's the thermodynamic equilibrium, a combination of three equilibrium, that is the thermal equilibrium, the mechanical and the chemical. Thermal equilibrium, temperature will not change. Mechanical equilibrium, P and V will not change. And chemical equilibrium, composition will not change. And when they all three will exist together, the system is said to be in thermodynamic equilibrium. So I can say in a thermodynamic equilibrium, macroscopic properties like PVT will remain unchanged with time. Chemical composition will not change with time. Equilibrium can be shifted in any direction by changing any of the variable by an infinitesimal amount. And all the changes can be recovered. All the changes can be recovered. Now, this is sufficient theory for the thermo, dear students. And now we go to all the various formulas which I am revising. Just see what am I doing now. I'm writing an isothermal process. And you all know isothermal process is that process in which the temperature remains constant. And hence, I will say that in an isothermal process, I know T is constant. So I can say delta T is 0, but I will say heat exchange, it is not 0. Because if heat exchange is 0, then how I'll maintain the temperature? Temperature is a function of internal energy. So I can say change in internal energy is also 0 because the internal energy will be constant. Correct? Of course, H is U plus PV. H is U plus PV. So I can say delta H is also 0 because change in enthalpy, delta H is delta U plus P delta V. We did the formulas. So that will also be 0. That is, whenever work of expansion is done in an isothermal process, then it is at the expense of supplied energy, work done by the system is at the expense of supplied energy, because when system will do work, it will become cool, but you want to maintain the temperature since it's isothermal. So whatever energy system has used of itself in doing the work, you will supply from outside. So work done by the system is at the expense of the supplied energy, and that is nothing but the endothermic process, because energy is supplied to the system, endothermic process. And whenever work is done on the system, then the energy will be evolved. Work done on the system is equal to energy evolved by the system, because if you are doing work on the system, then due to collision, the heat energy of the particles of the system is increasing. If it remains in the system, then the temperature will change. So you want the process to be isothermal. So whatever energy change or increase of energy has taken place in the system, you will just throw it out of the system. And so that is nothing but over here the exothermic process. The exothermic process. Now, we can also say that such an isothermal process can be carried out in a thermostat, where the temperature is static and constant. Thermostat, by thermostat, I don't mean it is thermally insulated. So this is not thermally insulated. Don't get confused. Because if it's thermally insulated, how can you make it endo or exothermic? Because heat exchange will not be allowed only in a thermally insulated. So thermostat is not thermally insulated. And for ideal gases, Boyle's law is applicable. You remember, Boyle's law was at constant temperature, pressure of a fixed mass of a gas is inversely proportional to its volume. And the entropy will change. So delta S is not equal to 0. There is change in entropy. And we can make the process, reversible. For example, expansion of gases is very, very slow, infinitesimally slow. So the process can be made reversible. So isothermal process can be made reversible. This full mathematical view of an isothermal process. Example, a very wonderful example which you will find in many entrance exams, like, evaporation of water, but not by heating, not by external heating, artificial heating. Evaporation of water in an open container using heat from surrounding. These are the examples I'm writing. Then fusion of ice at 277 Kelvin. Then isothermal expansion of an ideal gas and isothermal compression of an ideal gas. So these are the examples of isothermal process. Students, next we go to adiabatic process. As you all know, adiabatic process is that in which, first thing, mathematically, Q is 0. That is no heat exchange. We can also represent it by capital Q. Q is 0. Heat is neither allowed to enter nor leave the system. So obviously temperature can never be constant. That is, delta T is not 0. That is, delta H cannot be 0. That is, delta U cannot be 0. एडियाबैटिक, आप ना हीट अंदर आने दे रहे हैं सिस्टम के, ना आप सिस्टम के बाहर हीट आने, ना आप सिस्टम के बाहर हीट जाने दे रहे हैं. तो सीधी बात है, इफ वर्क इज डन बाय द सिस्टम, तो सिस्टम ठंडा हो जाएगा, कूल. एंड इफ वर्क इज डन ऑन द सिस्टम, तो सिस्टम गर्म हो जाएगा, हॉट हो जाएगा. बिकॉज when work is done by the system, it is using its energy and becoming cooler. And when work is done on the system, it is colliding, because you are doing work on it. Molecules are colliding, generating heat, but you are not throwing it out of the system. So system will become hot. So here, work done by the system at the cost of its internal energy. Work done by the system at the cost of its own internal energy, because you are not supplying anything. Q is 0. And here, work done on the system but just think, this is exothermic, so what it will be? At the wish of surrounding, that is, work done on the system will be at the or by the use of surrounding energy. So leading to increase in system's energy. Whereas here, it will lead to decrease in system's energy. So the endothermic adiabatic will lead to cooling, and the exothermic adiabatic will make the system warm. Another very important thing, students, it is carried out. Can you just guess? Yes, it is carried out in a thermoflask, a thermos, and not a thermostat. थर्मोस्टैट में टेम्परेचर स्टैटिक रहता है, और इसमें तो चेंज होगा क्योंकि आप ना अंदर एनर्जी लेंगे और ना बाहर फेंक रहे हैं. सो इट इज थर्मली इंसुलेटेड. It is thermally insulated. Boyle's law not applicable because temperature will change. And in Boyle's law, temperature is constant, but here temperature is changing. Cannot be reversible. It is not reversible. एक बार जो हो गया सो हो गया. Not reversible. Entropy is constant, so delta S is 0 because S is constant. Okay? For example, very, 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 very wonderful example. Working of an AC, adiabatic expansion, the AC, and adiabatic compression. Bursting of the bicycle tire. Bursting of the bicycle tire, adiabatic compression. Okay, let's move ahead. '22. Let us see the isobaric process. Okay, isobaric process. Let us see what it is. Now, children, first thing, isobaric means pressure constant. The moment I write pressure constant, I mean delta P, that is P2 minus P1 is 0. The moment I write this, I understand this is nothing but the process in an open vessel. You all know QP, that is heat exchange at constant pressure, is delta U plus P delta V. We have done this. So I can say at constant pressure, delta H, which is also delta U plus P delta V. So we can say QP is delta H. Not only this, work done is not equal to 0. And V will not be constant. So change in volume will not be 0. There will be change in volume because V is not constant. And say for example we can give a gaseous system. Example can be gaseous system, a gaseous system enclosed in a cylinder, gaseous system enclosed in a cylinder fitted with movable piston. Students, a very important thing in thermodynamic, piston is the mechanical link. So we move to next. 22. Isochoric process. Again, let us see it mathematically. Isochoric. So V is constant. So delta V is 0. So my dear students, W, which is P delta V, and delta V is 0, so W is 0. I mean P delta V is 0, so W is also 0. Now we know QV is, delta U, because if I take here P delta V, then this term is already 0. So QV is delta U. So I can say delta H is also delta U plus P delta V. This is 0. So delta H is delta U. So I can say QV is delta H V, which is equal to delta U. And we can say it is accompanied by change in pressure. So pressure will not be constant. Pressure will not be constant. So delta P will not be 0. For example, a gaseous system enclosed in cylinder of rigid walls. Gaseous system in a cylinder of rigid walls, or we can say a bomb calorimeter. Is an example of closed system, that is isochoric. Here, when I say rigid walls, I simply mean process in a closed vessel is no change in volume. Okay, so we go to the next. 23. I'm just telling you the meaning. It's not necessary in mathematical view, but still I'm just giving you the meaning. Reversible processes, something where the driving force Driving force is the force which makes the process occur, is infinitesimally greater than opposing force. Opposing force is that force which will basically oppose the process to occur. Driving force will help the process to occur, but opposing force will oppose the process to occur. That is a reversible process. This much is sufficient. Rest you please see the notes, our notes, and read from there. An irreversible process is that in which driving force, that the force which helps the process to occur, is greater than the opposing force, that is the force which does not allow the process to occur. This is represented by W max, and this is also represented by W reversible. This is represented by W irreversible. Now I've just given you the theory. Now I go to the mathematical expression for these. We just go to the mathematical expression. Next point I'm taking. Okay, now see. For the irreversible work, W is equal to minus P delta V. Derivation I've taught you in the class. I'm not doing the derivation again. We can also write it at W is minus P V2 minus V1, and we can also write it at W is P V1 minus V2. All of them represent expansion. That is, V2 is greater than V1. That is, V2 minus V1 is greater than 0. I mean delta V is positive. Now when compression is there, and since W is minus P delta V, so here I'll just complete the W will be negative for expansion. So that is, now when I say compression, how it will be? V2 is less than V1. So V2 minus V1 will be less than 0. So delta V will be negative. And when I substitute it here, the negative become positive, and so W will come positive for compression. And dear students, when V2 will be equal to V1, then delta V will be 0 and P delta V will be 0 and W will be 0, and this is a closed vessel. I hope this is clear to everyone. By here we simply mean the closed vessel. That is something like a bomb calorimeter. And so I'll just mention here once again, we have already done this. So the bomb calorimeter, which is in the closed vessel. Now with this, we will move to the maximum work. But again, I'll tell you, I'm not doing the derivation. This is only a revision of the mathematical formulas. And just writing here, A, expansion, B, compression, C here, when closed vessel. And students, one more thing that can come here is the vacuum, that is the free expansion. And by free expansion, I mean P external is 0. And so again, the P delta V will be 0 and work done will be 0. This is also called free expansion of the gas. That is, the work done in free expansion is 0. Now we move to next, 26th point. You remember the formula for W max was 2.303 nRT log to the base 10 V2 by V1. Minus 2.303 nRT log to the base 10 V2 by V1. This is expansion, students. Now the same I can write, from the Boyle's law, P is inverse to V, and on applying that, I can write this formula as, I'll just write it here, I can write it as minus 2.303 nRT log to the base 10 P1 by P2. An important thing, see, look here, if I change the sign, negative was expansion, I'm changing the sign, but there's not compression, wait. If I change the sign and I also change the ratio, see, I've changed the ratio V1 upon V2, still it is expansion. Same thing here, if I change the sign and I also change the ratio, still it is expansion. So all these 4 formulas are for expansion. Now I am writing compression. Let us see. Here, I will mention the formulas of compression. Now I'm making from here, just look here. I'll be making use of this formula. Just see. From there I'm writing. I change the sign, but I do not change the ratio. See, I'll write same thing. Ratio, I'll write same. I change the sign. You can just take care here. This minus, I have written plus. I change the sign, but I'm not changing the ratio. And then I change the process. It is compression. Now from this, I can make all. How? Look here. Now I'm making compression using the pressure term. So from here I can make this, I'm taking plus 2.303 nRT. I'm just making it from here only, from this equation. Log to the base 10, and I just write here P1 by P2. And from here, I can make one more. From here, I can make one more. If I change the sign, see, I change the sign. And I also change the ratio. Here, this. I'm changing the ratio also, P2 by P1. Still, it is compression. Same thing here, students. If I change the sign, see this plus, I'm writing minus 2.303 nRT log to the base 10. And I also change this ratio, this. Still, I am in compression. So that is how it is. I hope this is clear to you. Go to the next. the 27th point. The points of a cyclic process. In a cyclic process, delta U is 0, delta V is 0, delta P is 0, delta H is 0. It's cyclic. Delta T is 0. Work is not 0. Bhai काम तो हुआ ना, how work can be 0? A cyclic process carried out isothermally is called an isothermal cycle. Let's move next. So we've come a long way, students. And now I move to the next category of formulas, which will be I'm just taking the mathematical expression for the first law of thermodynamics. First law of thermodynamics. We all know the first law of thermodynamics states energy can neither be created nor be destroyed. That is, whenever one form of energy changes to, it will neither disappear nor something suddenly will appear, but only one form of energy can get converted into another form of energy. One form of energy will get converted to another form of energy. And there are other statements which you read from the notes. I go to the mathematical expression directly, which is delta U equal to Q plus W. And this is for compression. And same formula for the expansion will be delta U is equal to Q minus W. And for a small change, I mean for an infinitesimal change, the same formula can be written as du is equal to dq plus dw, which is compression, and du is equal to dq plus dq. When I say plus, I mean plus is the mathematical sign for the equation, but work of expansion is represented by minus dw, and this is expansion. Same thing you can write here also. You can take this mathematical expression plus, and you can write a minus here, which actually finally means for expansion delta U is Q minus W. Next we go to point number 29. which is first law of thermodynamics. Don't worry, I'm not repeating. This is something different. First law of thermodynamics and various processes. Let us see. When I say, I'm just coming, see. अब हमने सबसे पहले I take isothermal process. Okay. So, how will I write it? I know constant temperature, so I say T is constant. Okay. So I say delta T is 0. Now I know T and E, I mean U, internal energy, are function of each other. So if T is constant, E, or I can also say U, will be constant. If internal energy is constant, delta U will be 0. So in the first law, which is delta U equal to Q plus W, this is 0. So Q is equal to minus W. That is, for an isothermal system, heat absorbed is equal to work done by the system, or heat evolved by the system is equal to work done on the system, plus sign. Once again, I repeat, heat absorbed by the system is equal to work done by the system. Heat evolved by the system is equal to work done on the system. Let us see the next category. And that is the adiabatic process. So let us see how adiabatic process and first law we can understand. Now in an adiabatic process, children, Q is 0. So in the expression delta U equal Q plus W, I'll simply directly say delta U equal to 0 plus W. So delta U is equal to W. So work done on the system is equal to increase in internal energy of the system, and work done by the system is equal to decrease in internal energy of the system. Done. Next we go to the Isobaric process, which we have seen earlier also. Isobaric process. Now I know according to first law of thermodynamics, delta U is equal to Q plus W. Now in an isobaric process, we know at constant temperature, delta U is equal to, I hope you know, delta H minus W, because you know delta H is equal to delta U plus W. So delta U is delta H minus W. So that's another way to write the same thing. And I can simply say delta H is nothing but the QP, which we have already seen earlier. So I'll not go into the same detail again. Let us move to isochoric. In fact, we have done this also. No need to repeat. But let's just write one line at least. And that one line is, we know in first law of thermodynamics, delta U is Q plus W. And since it is isochoric, so W is 0, so delta U is Q. Come to the next, students, and that is we have done 29 pages by now. No, we've done 20 pages and we've done 29 formulas. Okay. Now I'm just recording, I'm just putting this recording to an end. And from point number 30, don't miss to see the next video, because these two videos will actually make you understand entire thermo. Bye-bye. See ya. See both the videos. Don't forget that. Love and blessings to all of you. Take care, my dear students.